In this review, I'm going to go through one of the components of the forest plot in the meta-analysis. At this point, I'm just showing you how to navigate through a forest plot. I'm not actually telling you either how to do it in the software or what's the statistical basis for it. So you can see here that I've opened REVMAN and I already have some data that I've entered. I double-clicked on this forest plot, which is in data analyses, and then it's within the comparison that I want to make. And you can see here that I have the meta-analysis. And as I said, I want to explain in this video this table. First of all, I have the first column, which is the study level information. Here I've just entered a study ID, but when I show you how to do it eventually, you are going to be able to either enter the author or the year or a variety of information. But that's what this is. This is the study ID. That's the first column. Then what are the rows? Each row represents data from a study. So this is the data from study 1. Let's go over to the next column. So the next column is actually a series of 2 columns. And what we have is the events and the total. Now remember, this is a PECA review, so I have 2 groups. Here I'm going to make a comparison of the seroprevalence in cattle to the seroprevalence in buffalo. If I was doing an intervention review, this group might not be cattle, instead it might be vaccination, and I would be comparing it to the unvaccinated. So these columns here contain the comparison. Now, if you're doing a prevalence review, this data setup isn't going to work for you. But we're just going to talk about an intervention or a PECA review because that's by far the most common and the easiest to explain in this first introduction. So here I have the cattle group. What I have in the first column is the events. That's the thing you're measuring. Now in this review, these people were measuring seroprevalence. So this is the numerator in the prevalence calculation. And this total is the denominator. So there were no seropositive animals out of the 301 who were detected, and in study 10 there were 141 seropositive animals out of 3,076 that were tested. In the next column, the comparison, it's the same type of data setup. So here's the number that tested seropositive, and here's the number that were tested. And if I wanted to, I could change those data, but I'm not going to. I'm just going to leave it like that at the moment. So we've talked about the first column, we've talked about the second set and the third set, and then we come here to the weight. This weight component is part of the meta-analysis of when we want to calculate the summary effect. So when we're going to try and combine all these data into one number. But first of all, we have to decide if that's a good idea. So I'm going to leave this weight column to when I discuss the statistical analysis. But that's what it is. It's a weight, and I'll come back to it. What's more important, on the other hand, over here is the risk ratio. This is called the effect size. So each study has an effect size. The effect that we're measuring is the risk ratio in this example, and its size is 0.4. Now, you know, because of your course, that in this example, cattle versus buffalo and the seroprevalence, that it is not actually a risk ratio, it's a prevalence ratio. But the software doesn't know that because software is written as standard. So even though it's called the risk ratio, it is actually, for this type of data, a prevalence ratio. If it was a cohort study, it would be a risk ratio. And so you can see here that I have an effect size, the risk ratio, for each study except for when it was not estimatable. So this is not estimatable because you can't divide 0 by 0. You'll see here that this was estimatable because the software added 0.5 to this cell, but it won't add it to 2 cells in the same row. No surprise here that this is the confidence interval of the risk ratio. Now you can measure the effect many ways. As you know, you could measure the effect as the prevalence, as the risk ratio, but you could also measure it as the risk difference. That's another way to measure the effect. Now maybe the risk difference is a better way to explain the difference in the prevalence, because remember, this is not a risk difference, it's actually a prevalence difference. Or the other way is the odds ratio. So let's just recall this is a prevalence ratio, and if it behaves exactly the same way for a comparison of prevalence, it's a ratio. So if the interval is consistent with 1, the conclusion is that the prevalences are not different. This says risk difference, but it's actually a prevalence difference. And if the difference was equal to 0, then that would say that the prevalences are not different. We could also use the odds ratio, but in this situation, I think the odds ratio is really not intuitive for interpreting the differences in the prevalence. So I would be inclined to stick with either the prevalence ratio or the risk ratio. So that is what I have up in this table.